this one. Good. Okay. Then I'm going to go ahead and then share the other screen for you guys to see. So this is kind of like this something that you see that this is a kind of like a talk I gave based on the principal component analysis about the visualization aspect, mathematical aspect, matrix aspect, and programming aspect at one of that med school over here. Yeah, it was given at in Tennessee, Queen College of Medicine. So in that one that I get started, something if you might gonna be interested in, this is the difference between the stat and the analytics, two branches of the data science. These are the major two branches of data science. Okay. So, okay, looks okay, that's good. Yeah. So then especially that when it comes to the elite scientists, data scientists are expected to be full expert in analytics and stat, both as well as the machine learning. Then mainly analytics help you to form the hypothesis. It improves the quality of your question, but statistics are is the part that you can answer improve the quality of the answers. So you have to have a broader knowledge on these two for sure in order to become like an elite data scientist at the end of the day. Okay. So look at that. We were somewhere here. Can you remember continuous and continuous when you have independent variable and dependent variable, continuous and continuous, we did the regression. And categorical and continuous, dependent variable, continuous, independent variable, categorical. That's where we are using the analysis of variance in another way that we did this one. Can you remember with the gender like a categorical X variable and the continuous variable like a weight or something like that, or height? Okay, we did that one. So analysis of variance or group regression. Okay. So the logistic regression, you have a categorical variable for the dependent variable, two options, yes, no, okay, on and off. See, like that, when you're going to send some kind of a data from one place to the other, like let's say that when you go online, when you have access to a certain page, let's say you're going to go to Google. When you go to Google, that from the central office, they're going to send some data. Data will be sent to you. Those going to come in a certain way called the on and off. Okay, some periods are on, some periods are off. Very similar to like a photons. Okay, if you have done that some kind of like a data processing classes, you know that how they travel in such a case that yes, on and off, logistic regression you can apply. And on the other hand, logistic regression, not only that, you can apply even that discriminant analysis as well. If you both are categorical, you normally use the chi-square distribution. Look at in the principal component analysis is used in diverse field. PCA, regression and data mining work together to solve practical problems in data analytics. PCA, principal component analysis, you're going to utilize in order to get rid of some unnecessary dimension, then get the regression, and the data mining is a part of these two. See? So it's exploded, correlated, regressive variable or independent variable, predictor variable, treatment variable, experimental variable, explanatory variable, or factor. These are all the names given you that this X variable. See? Regressive variable, independent variable, predictor variable, treatment variable, experimental variable, explanatory variable, factor to test the assertions about the data that appears and dependent variable, outcome variable, predicted variable, response variable, output variable. They all are the same thing. Select graphical, mathematical. See, they're going to select the graphical, mathematical, matrix, and programming tools. We have all kinds. Graphical tools, mathematical tools, matrix tools, programming tools for all phases of PCA, such as Artimax, Verimax, Equamax, Promax, rotations, diagnostics, and models. So pretty much that we're not going to do this one in detail because of that time constraint, because this is a very broad field. So when you see that printout, you can pretty much you have at this stage you can do just to explain just basically the basic stuff only. But in addition to that one, I'm going to show you that it's a graphical representation of the principal component analysis, and then you can then rotate the axis. They say that in our can you remember that GS excuse me, gross state product, GSP, that example, we have 13 dimension, we reduce that to 5 dimension the last one. And then 5 dimension, you can rotate. See, based on that one, you can get the maximum variation that can be explained by those variables, principal component. Okay, X like that. See, principal component is an unsupervised statistical technique algorithm, unsupervised. Okay, that means you are built in up. Okay, that means that when it's supervised, when you give the input, you get the, you can give the feedback, the output. But when in unsupervised one, input and output take together and they built up the model, That's what the machine is doing at the end of the day. Supervised one is that like a regression. When you give the feedback, sorry, input, they're gonna give you the output. In unsupervised one, based on that your output and input, to build up certain model. Dimensional reduction method, it reduces the number of variables that are correlated to each other in a few independent variables without losing essence of these variables. See? The number of variables, it reduces the number of variables that are correlated to each other. Okay, they correlated to each other, they can be reduced, fewer independent variables, okay, on see, other into fewer independent variables without losing the essence of these variables. Okay. It provides an overview of linear relationship between inputs and outputs. See, once you get the x1 and x2, as that we had like x and y in my example, but here x1 and x2, you can, once you that transform this one, you can get the new two variable called the PC1 and PC2. You saw that how we got these two, but we had no clue that why they were that in this direction and this direction. They were perpendicular to each other for sure, but what would be the angle? See, angle of PC1, how much would be the angle? How much would be the inclination with the x1 as well as x2? Let's say with the x1, once you know the angle with the x1, you know the angle with the x2, so it's not a big deal. Anyhow, you don't know the slope, you don't know the inclination of PC1, how much that should be. That's the one, in order to get that inclination, that's why we are calculating the eigenvectors. Eigenvectors are responsible for giving the angle. Okay, eigenvector, the component, two component, you can remember, I had a 1 over root 2 and 1 over root 2 for 1. The other one, and I had like a 1 over root 2 minus 1 over root 2. So 1 over root 2, 1 over root 2 are that the direction is determined by those two. Okay, same with the other component as well. So PCA help dimensional reduction, convert set of correlated variable to non-correlated variables. It finds the sequence of linear combination of variable. PCA also serve as a tool for better data visualization of high dimensional data. We can create a heat map to show the correlation between each component. It is often used to help in dealing with multi-collinearity before model is developed. Multi-collinearity is nothing but the correlation among the X variable or the regressive variable. That has to be tackled as well. Okay. It describes that data is good storyteller of its own. These models are useful in data interpretation and variable selection. Okay. So assumptions of PCA, independent variables are highly correlated to each other. They are highly correlated to each other. Variables include a metric level or nominal level. Metric means a quantitative, nominal means like they give the name that the quantitative and categorical. Okay, that's what it is. Features are low dimensional in nature. Independent variables are numeric in nature. Normally they are numeric, but you can use the Bartlett test. The Bartlett test is statistically significant as not variables are uncorrelated versus variables are correlated. You can run this test and see whether they were correlated or not. When to use PCA? Whenever we want to ensure that the variable in data are independent to each other. When we want to reduce the number of variables in a data set with many variables in it. See? Sometimes that you reduce the number, rather than reducing the number, you're going to reduce the normally the dimension. If we want to interpret data and variable selection out of it. It's a kind of like a combo. You're going to take rid of some variables that do not contribute that much to explaining that variation in Y, plus that you can just reduce even the dimensionality. So look at what is the relationship among the principal component analysis, regression, and data mining. We study all. In the big data environment, data mining and regression are often used together. Each has complementary strength. Data mining is the process of finding anomalies. In data mining, what we're going to do, you're going to find all the anomalies, trends, hidden inside, pattern, and correlation within the large data set to predict outcomes. See, when you see that then kind of like a correlation among that that your predictive outcomes, sorry, that your independent variables, you're going to use that principal component, and it involves use of the automated methods to discover new relationship in data. Useful relationship may exist among the variables. So the regression method of when causality needs to be established. Causal needs to be established and determines the relationship between the dependent variables and independent variables. And then when they are related to each other, we don't know if that's it's not perfectly the causal, because we don't know whether X variable is the only reason that the changes of the Y variable. The data mining, you analyze data, discover pattern, useful information, get it, and then go to regression. First you analyze data, discover pattern, get all the information, and then jump into the regression. Okay. In data mining, normally what are you going to do? You're going to find in the anomalies of the data, like outliers, missing data, some trends, hidden inside, like a hidden data, hidden variables that going to affect to our variable. There are some hidden variables going to affect to the variable. In factor analysis, we were talking about that. When you take an exam, that hidden skills going to affect to that when you get the grade. If you are sometimes really good in programming, not good in statistics, but some people they good in programming as well as in statistics. Some people really good in statistics, not in programming. But whatever that, based on that one, when some exams are given, your skills, which is hidden one, called the latent or masked one, will come into the picture, and then take care of that, all that give you the good grades based on that, how much skill that you have. But those skills are already masked. Nobody can see that one. Those are we can unmask by doing the factorization or factor analysis. You see that in some example, a custom analytic problem involves PCA, data mining and regression. Retailer collect massive volume of transaction data that describes customer behavior, purchases, promotions. Then you are thinking what variable might be useful of predicting the customer responsiveness. You're going to use the data mining to discover which variable and variable combinations are informative. That's where we are using it. Then you're going to use the logistic regression. That part we're going to come to that one. Logistic part, anyhow, you're going to do the regression later on. First you find the variables, then you do the regression. That's the sequence. That is the sequence. That is the sequence. In another way that we can see that I can show you here. Look at see here, look at this. That's a see. First, I don't know whether this can be. You should have this one to view. Let's go to the view. Why we cannot? Look at, see, it's a sequence normally, see, pre-processing, transformation, competitive regression, then compare performance. View, let's see, view, slide master, reading view. Here. So, see, file import, then you're going to filter data, then impute data if you're missing data. Then data partition, you can partition data. We can talk about this one a little bit because so that we can normally we're going to divide the data set into two parts. One part we're going to utilize in order to do the estimation. estimation of the unknown parameter. The other part we're going to utilize in order to assess the just accuracy of those estimates. Two parts we're going to utilize. Those are called that sometimes we have a different way of explaining those things, because that when it comes to that, at the end of the day, that to get the best model means this one, something I will add that one to here, especially that when we go to the homework number 3 back and then fish one, I added that one here for you to see. There are so many ways to have a look at it, get the best model at the end of the day. So this is not MSD sum squared. Okay, I'm gonna talk about number. Okay, I'm gonna little bit separate this one for you to see clearly. So calculate the press called the prediction sum of squared, where the press is nothing but you get the EI. I means like a without having that variable at that point, take out and then estimate. See, yi hat, take out and then take the difference between that one at a time. That's one square root. Can utilize this one too. We talked about the other day that the stepwise CP, but in addition to another two has been added to this one, archaic information criteria, and then Sabava, I think the Sava's Bayesian analysis, Bayesian criteria too. So in addition to that, you see here data splitting. See, I'm talking about here. See, data splitting N1, the size of the fitting sample used to estimate or fit the possible best model for predictions or forecasting. That's for that one. Then you have a N1 and N2. See, N1 and N2. See, you have a two. N1 for the size of the fitting sample used to estimate the possible best model for prediction of a forecasting. N2 the sample size of the holdout. The holdout sample used to assess the predictive availability of fitting sample. See, predictive ability of the estimated model using the fitting sample. These two. Those are the two we're going to utilize in order to calculate this something called the mean square deviation and mean absolute percentage. These two later on. And then with those one, we're going to go to their minimum values. Actually, three of them. See, models. See, data. Prediction purposes. You can use the press, you can use the MSD, you can use the MAD, you can use the MAP, and you can use the SBC, you can use the AIC, Mallows, and stepwise. Mainly these are the major ones going to utilize in order to come up with the best model at the end of the day. As I said, that's why that I'm here, that normally that in a when you carry out any real practical applications, so that when you are dealing with the data analytics, you definitely have to have a two data sets. The same data set you're going to split into two parts. One part you're going to utilize to estimate, the other part you have to utilize to assess the predictive ability of the estimated model. We're going to a little bit come to that one. Those are the things that we were talking about here. Data partition, transform variables. See, we talk about transform. Then you can do the cluster. You can divide the two stages: variable selection, principal component. See, look at after transform variable. See, then you can go to cluster analysis, two-stage analysis, variable selection procedures, then segmented. See, so then see. Domain regression, see partial least square regression, last, see, then model comparison like that. So this is the way of doing things at the end of the day. But we systematically lay down like a little bit foundation for you to move forward. But at the end of the day, you're going to get everything together and then analyze. Okay. That's why piece by piece, we're going to do regression part. We're going to do principal component part. We're going to do logistic regression part, like that. And cluster analysis, that's kind of imputation, filtering, like you like a kind of like idea. So then later on, you can, once you are done with all the courses, you can pretty much carry out the data analytics, so that all the data analysis we going through this process. Okay, it's important because that's a very important. So variance summarize the sum of the application of PCA. PCA can be used in image compression. Image can be resized as per the requirement and pattern can be determined. Okay. PCA helps to customer profiling based on the demographic as well as their intellect in the purchase. PCA technique that's widely used by researchers in the food science field. It can also be used in the banking field in many areas, like applicants applied for loans, credit cards, etc. Customer perception towards the brand. It can also be used in the finance field to analyze stocks quantitatively, forecasting portfolio return, also in the interest rate implementation. So PCA is also applied in the healthcare industries in multiple areas, like patient insurance data, where there are multiple sources of data and with a huge number of variables that are correlated to each other. So PCA is using that to analyze those kind of data in that field. So variance summarized means the variance is summarized through the something called the scree plot. You saw the scree plot. That's the plot between that eigenvalues versus eigenvalues versus factors. It is an eigenvalue where the maximum variance reduction take place, and then next reduction and so on. Now to identify how many pieces to take into consideration, we will use the scree plot. Plot scree factors, see, on x-axis. See, scree factors means principal component. And eigenvalues in y-axis. Factors can be extracted based on the two methods. So how many factors to be included can be determined by these two methods. Elbow method. According to elbow method, we consider the value where the elbow is created in the scree plot. In the scree plot, but pick up that value. But we have a big disadvantage. There are so many elbows. Elbow method is that a scree plot can create multiple elbows. This makes it confusing to select one eigenvalue. So because of that reason, they jump into something called the Kaiser-Gutmann rule. See, according to Kaiser rule, values less than 1 should be omitted in the scree plot, and the retained values are always greater than 1. This rule is mostly used as a well-known method to identify eigenvalues from a scree plot. Okay. So when you partition the variance, you are partitioning the variance in this whole setup. You go to the factors of component, factor analysis of principal component, square each element, then you get the square loadings. We talked about the loadings the other day. See, loadings, we talk about the loadings. Then sum down items, then you get the eigenvalues PCO, sum of squared loadings. You see this one, see, in the factor analysis, partial analysis. See? So the principal analysis of the factors, okay, this one, communalities, see? Across the factor, sum down items with the sum across the factors. Then again come back, you get the total value, sum down factors and sum down items. I can show you that how this can work. It's the same thing we were talking about. So this is where that the place of this in the very beginning people were talking about the PSS. Now that these two, Python is becoming that major. Actually, R is playing a heavy role too. But see, Python is that major language that dominating, and then along with R. Okay. So like that. Okay, a little bit that for you guys to get a rough idea on that one, and then let's go ahead and open this one, and I'm gonna show you here. First thing that before you even go to that one, I want to tell you that the other day, can you remember that when we were talking about the variable selection, that's not the right one. They had a wrong one over here, k squared. K squared. It's not the all possible number of all possible Why I cannot get this one over this one? You can see the. I can open again. This one. Variable selection. Variable selection we can remember here. So we say that see, if there are k x variable to consider using, there are k squared. No, it should be 2 to the k possible subset. 2 to the k. For example, with only k equals 5, there are k to the 5 32 regression equations. 32, not 25. That was wrong over there. So then we come to our example. See, we were talking about that. This is the example we talk about under that possible, all possible regression models. This is 1, 2, advertising, bonuses, market, and competitor sales. So these 4, that means you have a 2 to the, sorry, there are, we are not using region, therefore there are 2 to the 4, which is 16 regression equation. That's how they got the 16, not the 4 to the 2. They made a mistake. Whoever wrote their book, it's not right. It should be 2 to the kx. 2 to the how many regressive variable? 2 to the x 16. You saw 16 here. We have 15 plus the empty model. Okay. So that's why when we were going through this one the other day, our example, can you remember fish example related to homework 3? Homework 3. Homework 3. Homework 3. All possible. All possible. See, all possible. See here. Can you remember that? If I run this one a little bit one more time, data, work, fish. Okay. Fish data, we have like a weight, length 1, length 2, length 3, and height, width, and log weight. All so if you run this one, see, regression, you can remember that regression very easily you can get. Yeah, see, these are the outliers, everything. See, residual, look at the residual versus the predicted value. See, normality assumptions, not being even, that satisfies so many things that we can discuss over there. But anyhow, that this the regression models in height with I utilize only that in quantitative variable only, metric ones only. Then we saw that there's a one called the species. See, when we introduce this one, and then species has to be introduced because of we have to introduce that one. Then maybe the numbers 4, 5, and 6. Okay. So we created a new variable called the spec for the species, and then we were looking for the all possible one. Okay, all possible ones. Say length 1, length 2, length 3, height, width, and spec. Then 1, 2, 3, 4, 5, 6. Since there are k6 regressive variable, length 1, length 2, length 3, height, width, and spec, there would be 2 to the 2 to the power of k, which is 2 to the 6, which is 64 possible. That's why the other day that we saw that there are 64 possible regression models. Can you remember that here we were calculating 64, then we came up with a 64. Well, I'm gonna get rid of this one and then open while we are opening this one. We can discuss about that one. So we had a 64, can you remember 6 choose 0, 6 choose 1, 6 choose 2, 6 choose 3, we did that calculations, and then we ended up with 64. Then we were wondering why that it's not gonna that that line with what they have suggested. They say that if you have a 6 regressive variable, it should be 36, but we came up with the 64. That is the reason is it's not k to k squared. It should be 2 to the k, not the k to the 2. It should be these should be that switch k to the second. Rather than k to the second, it should be 2 to the k. So 64 possible regression models, we saw that for these 6 variables. See? Even with that one that we normally suggested that this square and adjusted R square had a very peculiar that characteristics. The more variable you're going to add to this one, the higher that correlation determination of coefficient would be, which is R square. So that one, that's not a good thing, that whether when you're going to increase that one, R squared going to go up in most cases, and by you will be that kind of like a misled by looking at that one thinking, oh my god, okay, R squared is higher, because of that reason I'm going to go ahead and pick that particular model. But there might be some more variables that are not important at all of explaining the variation of the weight. So those variables to be taken out. That's why we're going to jump into some procedures called the forward selection and backward selection. That set by selection. Okay, I'll show you that. We were calculating this. And can you remember? See? This one empty models for this one 6 choose 1, 6 choose 0. It should be 6 choose 0. 6 choose 0 is nothing but definitely 1. No, 6 choose 0. See? 6 choose 0 is 1. So here we have 1 plus 15 plus 20, 15 and 16, then 20, 30. Here 15, 56, 62, 63, 64. See, total number of regression model 64. It's very aligned with, see, 2 to the 6, which is 60. See, same thing. So when you calculate, you know, the singles, we have that empty model 1, all 6 going to be only 1, 5 variables going to be, there are 5 combinations. If we have 4, there are 15 regression model for 3 variables at a time. You have 20 of them, 2 like that. See, this is, you see the sequence. This is like the numbers going to be in the, this is a Pascal triangle. These are numbers coming from the Pascal triangle, actually. You can see that very clearly. 1 and 1 at the corner, and then 15 and 15 in the, if you have a 6, they go like that. If you have a something else, that 5, it's like that. It's like a triangle. And then that this coming from this one. See, in the beginning you have 1 here, then 1 and 1, then put 1, and then you add these 2, then 2. And you add these 2, 3 and 3, and then you're going to add another 1 and 1 to the beginning and the end. Then you're going to add this one 4, this one 6, this one 4, and add 1 1 like a triangle. Then you add this one 5, this one 10, this one 10, this one 5 and 1 1. See? Then later on, see this one. Hi Angela, we just started. Okay, we keep okay, you're not gonna miss that much because we just I recorded everything. So this one is 6, this one is 15, this one is 20, this one is 6. Oh, sorry, this one is 15, this one is 6 and 1 1. See? So that's the same thing that you saw that side. See? 1 15 20 15 6 1. 1 6 1 6 15 20 on one side. So that's called the Pascal triangle. 2 3 4 5 6. This one, when you have a 2, is on 1 variable, 2 variable, 3 variable, 4 variable, 5 variable, 6 variable. That's a combination. So here, see, this is for the 1 variable, this for 2, this is for 3, this is for 4. I'm sorry, I started wrong. The last one for the 6, okay, 6. This is for 5. See, I go like that. This is for 4. This is for 3. This is for 2. This is for 1. Okay. Not this side, the other side. See? Like that. See? 1, you have 1, 1. See? 1 variable. See? 1, 1. Combination. See? You have a 2. See? 1, 2, 1. 3, 1, 3, 3, 1. 4, 1, 4. 6, 4, 1, 5, 1, 5, 10, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. Next one, 7, 21, 35, 21. Sorry, 35, 21, and they were symmetric. Okay, that's called the Pascal triangle. So anyhow, it's not a big deal, but if you looking into that, those numbers that, so that's something that I want to bring to your notice as well, because of the way that they have put over there, they make a mistake. Okay. So here we have a 16 for a reason, 2 to the 4. Okay. So they were, then when we get back to this one again, and let's look at this one. Okay, now we're going to talk about the all possible models. Okay, we're looking into all possible models, and then based on the adjusted RZ and CP and RMS forward selection. See, in addition to that one, that you can look into forward selection. See, by itself, by you don't have to go to the reg. Using the reg, you can do that one. Let's see that with the reg we can get the forward selection. This one all possible. If you use the forward selection only with the reg, would that work? See, eventually you have a length 3 and intercept only being that selected. Oh, sorry, no. But they have it. Summary of the forward selection. This is the summary. Plane 3 with spec and height. See, those are the ones gonna have that at the end of the day. See? See? Those are the ones you're gonna have at the end of the day. Let me see. See, you can just simply put F, and you can simply put the some significant level of entry, which is 0.05 entry, because you can remember the forward selection. You're gonna start with that. The variable which is highly correlated with y. Okay, you can remember that, and then you keep adding that one. You keep adding only. Then you're gonna come to 2. You're gonna add another one and keep going. We had that discussion. Okay, so backward elimination. See, that backward means you are trying to take out. That means they are trying to stay there. Significant level 4 stay 0.05. So see, backward elimination you can do separately if you want. Let's say that we're gonna come up with the same thing. See? At the end of the day, these are the backward elimination. Oh, sorry. Where the elimination step 2, step 3, condition, see, length 1 and length 2. See, 2, 3. See, length 3, height, width, and spec. Pretty much the same thing that we had for that one. So then stepwise procedure. No, this is not the right one. I think this is not something gonna go here. Okay, this part from here to here. No, but procedure, and it should go here. Yeah, correlation is based on that one. Okay, see. Then stepwise selection, you're gonna put the both significant level for the stay and enter. Both. Let's see what you have. length 3 and intercept. See, others are taken out. No, that means, oh no. Let me see. Step 3, still step 3. Step 4. Yeah, at the end of the day, see, intercept, length 3, height, width, and spec. 1, 2, 3, 4. 4. Length 3, height, width, spec. Pretty much in all these three methods produce the same thing. Produce the same thing. Produce the same thing. Okay, stepwise. So if you want, you can go with the other. I have that one over here. See, so GLM selection procedure too. See, either with that one you can get this done too. See, or with the regression you can go with the rig and one at a time. See, then if you want, you can go with the regression with the R squared. You can keep the best certain number of the best of them. R squared adjusted. See, selection procedure. See. So highest R squared means like R squared means a pre. It's called the pre. Pre is nothing but sum of square regression divided by sum of square total. That can be written like 1 minus SSE over SST, or you can write in the F statistics times the no, that should be degrees of freedom of regression divided by F times degrees of freedom of regression plus the degrees of freedom of error. There's another way you can write that one too. See? The same thing, R squared. See, you can write in terms of this degrees of freedom and F as well. So with that one, you can go to you can go to that one and then get the one with the highest correlation. As I mentioned earlier, that you might be misled by that by looking at that highest correlate the R squared one. You try to pick up even if some variables not gonna very importantly explain the variation of white. So this is not a good criteria. That's why we're gonna jump into the. We're gonna show you that what would be the best one. Then if you want to go to the R squared selection, this one, that's the same thing. Yeah, highest R squared or coefficient of determinant selection procedure. Is that the same thing? Highest R squared coefficient of determinant selection procedure, which is that. Yeah, this one we do not need. That's the same thing. Done. This one. Then adjusted one too. You can go to the adjusted one given by the R squared. Adjusted is nothing but 1 minus mean squared error divided by mean squared total. And then you can say that for the selection procedure, you can get the H star with a certain number of best, how many you want to have a look at it. And then you go to the Mallows one, see, you go to the Mallows one only. And then something called the Akeiki. These are very powerful methods. These are the very powerful method, not those ones. Akeiki and the Mallows very good, not the R squared and all kind of things. Smallest Akeiki information criteria as a selection procedure, which is Akeiki AIC is nothing but the total number of observation terms ln sum of squared error divided by n plus 2k. See, 2k stand for the number of recursive variable. You know that one. So you go to the smallest one. Let's say that how it's going to work. Oh no, what happened? Okay, selecting one of the following R, B, Q. Oops, sorry. What happened? AIC. Why they don't have AIC? Let's see. No. Why they don't have AIC? Okay. Oh, sorry. Here is the problem. Okay, information criteria. I have to give the number. Let's say 2 or something. So, no. Forward max syntax statement will be ignored. Okay, let me see. Why? Selection AIC. Okay, one. This one is why I wrote this one several times. Smallest one, length one. k, 2k. It's the same thing. We don't need this one. Okay, the other one is this one AIC. The other one is SAVAS. SAVAS one AIC. You can put the AIC should work. Why it's not gonna? I'm gonna get rid of this one too. Okay, the other one SAVA. SAVA. You put SBC. SBC. SAVA's Bayesian criteria. SBC. Let's fit the two. Let me see what happened here. Selection. 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 They're not going to show that selection. That should work. Selection CP. CP. We try this one too. Yeah, CP1, CP1, 2, 2, 2. Oh, that coming with only the CPs. See? Only CP gonna show for the 4 variables, 5 variables, 6 variables. See? 3, 6 variable only 1, 5. They've been ordered, I think. See? See? The smallest to all the way to the highest. See? Regardless of that the setting. So if you're gonna put like that way, 2 selection, I put, let's say best, let's get best equals 2. This one. Then you go to the lowest one. 2, 2. Get them to show 2, 2. Yeah, 2. The best 2. See, best 2. One with the 4 variables, which is length 3, height. That's the same thing we got. This, which one has the lowest one? So if you put like a that, you're not gonna put anything. It's gonna show pretty much everything. Let's say that give me the 2 best ones. They're gonna show the best 2 best one for the CP. Here they're gonna give the 2 best one. If you want 2 best one here, then this one 2 should work. That even the archaic should work too. I don't know. Let me see. It was working earlier. Oh. R square. R square. Why it's not working? R square. R square. Let me go. Selection. They don't take like a R square. They don't take like HR square or R square with this one R square. So the one. Let me see. Okay. R square. The 2, the 3. Then this one. Go with the highest one, 2, 2. This one give the 2 to the last one doesn't have that. This one, see, it looks like, see, this one can, even though that we're not going to plan to pick that all of them because that's we are trying to reduce. See, I think this one is the one that when going to compare contrast with the CP and everything together. This is like just a standalone. Can you remember? And then this can be even verified. Let's say, for instance, that by accident that you pick this one. Now you were thinking, would that be the best model? How you can get this verified through the other method. Through the other method. That's R squared is not that much of a like a very powerful way to that method to or that criteria to select the best one. The more variables you throw, that the higher the value of the R squared. And even though there's some variables not gonna very clearly or importantly explain the variation of the weight over here. I'm gonna see with this one whether it's gonna work too. Let's try this one and see whether it's gonna work. Still not valid. Use the proper order. Let me see what that means. Work, fish, weight, length, selection, HR square. I don't think it's the same thing. Let me see. They give the best one. See, look at the now when you go to the R square digester, it's gonna come up with the 4 variable one. See, 1, 2, 3, 4. Pretty much they both have the same R square adjusted, but when you compare contrasted with the R square adjusted R and CP and pretty much everything that, yeah, at the end of the day, what would be the best criteria? We check with this one. We had an issue with this one, AIC, you know. Why it's not gonna work? Okay, I'm gonna get this down. What? Syntax expecting one of the following adjusted R square B backward CP forward max minus R square. How come? Why they don't have this one? AIC and SBC. They both. Just selection procedure. No, they ignore that one. Amazing. Why is that? They were looking for the other selection procedures. But okay, let's keep these two for time being, but those are the very important ones. Then see, there are 5 most common that methods for selecting the best model. Pick the best model by the stepwise method with the alpha, okay, alpha means that I can say with I would say SLE. I can say SLE, significance level of entry, 0.2 and significant levels of stay. See, entry and stay. Entry we are using in order to enter. Stay we are using when we use the backward elimination. You started with that one, you trying to not to get out, you try to stay there. So if you use with this one, that would be the best, pick the best model with these criteria. And pick the simplest model using the Mallows one, that we know that now. Pick the model that minimizes the AIC. Pick the model that minimizes SBC. And the 5th one called the press. Press is nothing but prediction sum of square, where the press is sum EI. EI means like that, normally that, see, if I show this one to you, press, I'm gonna show this one to you. See, you can see press means that, see, summation of yi minus yi, see, minus 1. See, yi, see, where yi comma minus 1 represent the prediction obtained from a model estimated with one of the sample point deleted. You have deleted one sample point and its corresponding x, 1 point has been deleted. Okay, so you go to that one, see, this has been estimated with that one. See, where yi comma minus 1 represent the prediction obtained from a model estimated with one of the sample point deleted. The prediction is obtained by evaluating the regression equation at xi, but the data point xi is not used to obtain the estimated regression equation. See, the prediction is obtained by evaluating the regression equation at that point xi, ith point. See? But the data point is not used to obtain the estimated regression equation. When you're gonna, they estimate that one, they have not used this guy. They haven't used this guy. Without that one, again you go back to the same place and say, hey, my yn then without me, when you estimated that value, that gap you're gonna check. Normally you have y minus y hat. Y is like a without y is a any point. Okay, any y variable, in that case weight. Okay, weight. Okay, weight, let's say weight. But y hat I minus 1 means like a that you have calculated that estimated that guy without one point of that other variables. Other variables without have taken into account that the weight. Let's say that we're going to related this to simple regression. Weight has been given with respect to the length without that length, but at that point we take that y out and then estimate it and get that y hat, and that y hat and y you're going to take the difference called it that difference called this that prediction errors. See, prediction errors. Then you're going to square that one and then sum them up, called the press. Let's call the press. Okay, that's called press. But you go back to that one and estimate again. See, that's the same thing I wrote over here, and then choose the model with the smallest press. In addition to that one, you can doing that sixth method by looking at these criteria too. See, measure these criteria. You're gonna split your data. Okay, you're gonna split your data. And on the other hand, that I have to show you something here too. One more thing. See, look at thus as with the use of that validation sample. See, predictions are obtained from the data. See, validation sample. Sorry, I'm here. Okay, I come here. Okay. See, look at. You're going to fit in, you get the data and you're going to get the data and you split that one into two parts. One you're going to utilize for the fit-in data, and then one is used to that estimate of fit possible equation for predictions. See, that N1, you have the data set, you're going to split into two parts. The other one, hold out sample variations. See? So we used to that assess that prediction ability of the model estimated using the fit-in sample. This is the fit-in sample, this is the higher hold out sample, same sample. Then you're going to calculate something called the mean square deviation. Look at, you get the y minus y hat, but you divide that by n2. You're going to do that one only for this data only. You're not going to use the whole data set. You split into two parts. When that one has been already utilized, let's say that you have a 10 data points, 100 data points, you have utilized 30 to get this done, okay? And the rest leftover 70 being utilized over here to get this done. So with the aid of that 30, you calculated that you came up with that estimated model y hat. That y hat, you're going to bring it over here, and you're going to do that one only for the data, available data for the other 30 or 70 data points. See, that's a 70 data points, and then you do that, you're going to fit in into that same model, but you use not the whole thing. Now N2. That's called the mean square deviation, called MSD. And in a pretty much similar fashion, instead of doing square, you can get the absolute value. Absolute value. That's called the mean absolute deviation and divided by N2, called the MAD, MAD. Or you can get the mean absolute percentage. You get the absolute value, see, the percentage, see, percentage. You get the percentage and find the mean. See, you get the mean, you get the absolute deviation and get the mean. In order to get the mean, you divide by the number of observation in that particular hideout sample. Okay. See, here too, mean. What kind of a mean? Square deviation mean. Square deviation. Squared and deviation. This deviation has been squared. Okay? You don't have to say sum. Sum has been divided by n2. That's called mean. Okay. If you don't have a denominator, you could gonna call the top part. Simply, you can call the top part sum of square deviation. That sum part has been seen divided by n2. No longer you call the sum, you call the mean. That's why we have a mean square deviation. That means that sigma notation and n2 being go together to say mean square deviation. Same way, mean for n2 and sigma notation together, mean absolute means this sign instead of square and deviation. And the same way, mean has been used to n2 and then this whole thing, see? Okay, absolute percentage, see? This is the absolute percentage. Look at the percentage. Absolute value divided by the absolute y divided by n2. That's called the mate. Okay, so based on those, you calculate those three. Out of those three, see? Out of those three, you can go to the mean square deviation, smallest one. Mean absolute deviation, smallest one. Mean absolute percentage, smallest one. Okay, like that. Okay, so that those are the very powerful techniques utilized in order to get this done. Okay, this one we already did that one, but I would like to add this one at the end of the day. If you want to pick that best model, stick to this one. Stick to this one. These 6 methods. Especially, you don't have to worry about forward or backward. Go to the stepwise with these two. Go to the mallows. Go to the AIC, SBC. I want to double check this one. Okay, I see why it's not working. That's a very powerful method. These two are very powerful. That Akeiki and Sawa. I think both are Japanese statistician. Akeiki and Sawa. Patient criterion procedure. See, that's the formula. Okay. So press one we have written in the formula. Like that. So the other method that especially R squared is not a good way to have a look at it. R squared adjusted. Those are not in the very beginning we were looking at that one. No longer we're going to look at that one. And on the other hand, on top of that one, that now we're going to look into the principal component. That's the one we were talking about over here. See, can you remember that in this principal component analysis? See? Discriminant analysis, logistic regression, principal component. In the principal component analysis, can you remember we were talking about this one we talked about the other day. Okay. Then let's get this data one more time. Principal component analysis. We did that one in a certain way up to certain point. Before go to that one, we did this one. I want you to see this one, and then mainly physical interpretation. I'm going to show you something here. Freeze all the time. Cannot do nothing. Freezing. So while this is in open, we can go ahead and look at this one. Yeah. Okay. Then this one, principal component analysis, we did that one. And up to certain point, the factor analysis. Can you remember factor analysis? And I would like to go with the discriminant first. Okay, let's go ahead and look at the discriminant analysis. Okay, the same thing. We're going to go through all these. Okay, so look at that. These are qualitative dependent variables. When you have a qualitative dependent variable, you use the discriminant analysis and logistic regression. Qualitative, okay? Qualitative dependent variable. We haven't done anything like that so far. Principal component analysis is a different thing because we had all the regressive variable. We wrote the linear combination of the regressive variable to get the new dimension. When we have a 13 variables, we really wanted to work with the 5 last time. So let me see that something is before. Let me see. Okay. This one. Okay. Principal component analysis. This one analysis. Okay. Let me see whether it's here. 126. What do you have? 126. 126. No. Let's check this one. No. Let's check this one. 126. Another one, 126. Let's see. One 26. Because it's in the book, then I don't have to write this one again and again. Number 4, number 2. This one. And 26. Simple interpretation. This one. Not this one. Yeah, that's the one. That's yeah, this should be here. 140, 126. Here. 126 here. See. Let's say that your x and y, okay, that the way that I took from that example, can you remember in this one? See, in the beginning that I took example for, see, this is a sample, 1, -1, 0, 1, -1, 0, 3 points. So I locate those, okay? I'm going to go ahead and locate 1 and -1. See, this x-axis, this y-axis. Let's say this is a test 1 and test 2, 2 tests. Okay, regressive variable. The y variable not mean, y means a response variable not in on this dimension, okay? So 1 and -1, see 0 and 1, 0 and 1, and -1 and 0, see? Okay, and then their center is 0, 0. So what I'm doing over here in principal component analysis is I'm looking for a line. Okay, what we're gonna do, we are looking for a line to which that we're gonna draw this projector. See, we're gonna see, make the projections. See, projection, perpendicular projection from each and every one, and see each and every one, and we check. Then we have a 2 distances. Okay, this is a projection distance. See, from here to here, from here to here, from here to here. On the other hand, we have another distance to same thing. From the center to the projection, the point of projection of this point. Point to the projection, point of projection to that distance. Point the origin to the point of projection. Origin to the point of projection. Origin to the point of projection. Or you have this, see, the point to the projection point. Point to the projection or origin to the point of projection. Point to the projection point or origin to the point of projection. 2 ways you can have a look at it. One becomes minimized, the other one becomes maximized. Okay. See, you have to make this one minimize, or you have to make this distance maximize. I'm picking only one point over here. The point I call that one B. I'm going to call this one point B, which is 0, 1 point for my convenience. I don't have to go working on all the data points. I'm going to go to 0, 1 point. I'm going to label it as B. Then I'm looking into 2 things. I'm making like a perpendicular projection to a certain line. Okay, this line, one of the line. Let's pick one of the line. and then make a projection. See, you make the projection. And then you have a two distances from here to here called the point to the point of projection, or origin to the point of projection. You have to look for the line which passes through this origin, passes through the center. That would give you the minimum of these distances, or maximum of these distances. That line is referred to as the, see, principal component. So I'm picking again, and I come back to that one and then focus on that one only. So this distance, I thought that, okay, this line would be that one which produces for all the points, okay, not only for this point, for all the data points. When you're gonna project on this line, that would give you the minimum distances on, if you're gonna project on that. Look at this one. Sometimes, see, this one maybe, see, larger, and then when it comes to the other points, they would contribute in a different way and then make that summation the larger. So I need the minimum this point, this length, or maximum this length. Let's say that that's going to happen with this particular line. This particular line. See, this particular line. See, so this one to this here, this B has to be minimized, C has to be maximized, this to be minimized. That line is this one. That's your principal component one. So this line, that's the distance. That distance I'm gonna focus on this maximizing C, from the distance from the origin to that point, which is, I'm gonna square 2. I get the distance and square, because when you sum them up, they will add to 0. Because that reason I'm gonna square. I'm gonna get the point. Okay, I'm gonna get this one like this. Okay, I'm gonna have a 0, 1, 2, 0, 1 to this. See, based on that one, this line, that means that origin to projection of this one. Okay, which is origin to projection of that point related to this one is this one. And the origin to other point somewhere here. Can you remember? Somewhere here. That distance is here. Okay, this distance. And there's another distance being hidden over here, because I can get a visualize that what I'm talking about. So I'm simply looking for all the distances from the origin to the projection point of each and every data points, and then square them. Then we call the sum of square distances. And you are looking for a line that maximizes the SSD, which is for the principal component. You're looking for a line, and then you're going to get its counterpart, which is perpendicular to that one. See? Sum of square deviation for PC1 is nothing but eigenvalue for PC1, which is 1. Can you remember? Then you take the square root of the eigenvalue of PC1. It's called the singular value for PC1. The singular value of that one is nothing but this one. So this line has a, see, this one carry the variance of this much. See, that's why we are trying to see sum of square deviation for PC1 is nothing but the eigenvalue. Sum of square deviations. See, this summation. See, SSD for PC1 for the principal component one. I'm talking about this line, okay? With the aid of all the points, sum of square deviation, sum of square the distance has been calculated with the aid of all three points. That one is nothing but principal eigenvalue, which is 1 in this case. And the SSD for PC2 is the eigenvalue for PC2, which is 3. Its singular value is square root of that one. See, when you draw, look at the PC1 over here. It's perpendicular PC2 over here. We wrote the PC1 and PC2 with the aid of the eigenvectors 1 over root 2 times x plus 1 over root 2 y, that's PC1. One of this one is nothing but root 3 over root 2 x minus root 3 over root 2 y. See, look at PC2. That's a graphical representation. This is related to lambda equals 3. This is eigenvector, eigenvalue. This is eigenvector. This is the eigenvalue. This is the eigenvector. You see, 1 over root 2, 1 over root. Who will determine this angle? The eigenvectors has two components. They will determine that. How do you get that one? You're gonna this part for the run, this part for the rise. So in order to get the slope, you know, run divided by rise. Run divided by rise is 1. 1 is that tan angle is given by the tangent. So you take the tan inverse 1, which is 1. See? Which is, I'm sorry, it's 45. It's not 1. This should be 45. 45 degrees. See, that's why 45 degrees. It depends on whatever the value you have over here. If you divide this by that, again, root 3 get cancelled off. You get the negative 1. That means 135. 135 this angle with respect to this guy. It's very mathematically consistent, graphically consistent, matrix-wise consistent, program-wise consistent. See, PC1 and PC2. So these two will determine the angle of this guy with respect to this x. That means this is your rise, sorry, run. This is your rise divided by run. This is your rise divided by run. That will give you the answer. It's the physical interpretation of that one. Later on, we decided based on the lambda Kaiser value. I showed you earlier. Can you remember Kaiser criteria? Elbow method and Kaiser, according to Kaiser rule, values less than 1 should be omitted in the scree plot and retain the values are always greater than 1. This rule is mostly used as well-known method to identify eigenvalues from the scree. Scree plot is nothing but the plot between the eigenvalue versus the principal component. You saw that one when we were running that one. So that's why we decided to keep the one with the lambda equals 3 only. Lambda equals 1 can be taken too, but since we are trying to reduce the dimension, you can only work with this guy. This is your new x variable. See, you take out lambda equals 1. This is PC2 will be utilized to explain the response. Then you fit that one into regression line or plane, doesn't matter. Whatever, based on that, how many you have over here. See? So on the other hand, you know that the sum of variance of x and y, sum variance of x plus variance of y is 4. Covariance matrix, go to the covariance matrix. See, go to the trace, that's the same thing. And go to the communalities, that's the same thing. Go to the sum of eigenvalues, that's the same thing. Sum. You are talking about the variations, variance. All variance. In any direction, you can get the variance. You can calculate the variance of x. You can calculate the test 1 and test 2, or x and y. I'm not talking about y means like this is like x1 and x2, two regressive variable, okay? So they are summation 4. Trace go to this one. You know how we created this one last time. So see, then proportion is how much? Proportion being explained by that principal 1 over 4. Your total is 4. Each one has how much? See? Eigenvalue is 1. 1 is the proportion. 1 and 3. See? 1/4 and 3/4. And on the other hand, you got the when it comes to our example, we saw that how we got this. The age, this one, the max pulse, principal component. So the PC1, the age, weight, run, pulse, max pulse. I mean, like it's based on that. This principal component is based on that. What we were trying to do over here. Homework 4, can you remember? Homework 4. Can we get this data? See? Weight, oxygen, runtime response, response. Data, rate, partial, this one, regression print, stack analysis, and principal component analysis. For that, that's for the other one. Okay. We can run that one with factor analysis. For this one. That's it, principal component regression. You can go straight to principal component regression. Or there are 4: age, weight, max pulse, PC1, L1, L2, 4 of them. See, since you have a 4, PC1, PC2, PC3 in that particular example, let me see how much we have. 1, 2, 3, 4. Age we have selected by age, weight, only 4, not 4. No, we have 6, no, but we selected only 4 for reason. Okay, you know the reason why we selected 4, because of that. If you want, you can run the principal component analysis for this one. Just say that. Okay, let's go and then get this PC regression, discriminant analysis, principal component analysis. This one. Let's get this one, and then copy and then go to homework 4. Homework 4. Principal component analysis based on this data or this data. That's what I was talking about. That any data set you have. Okay. So since I have selected this data set, rather than doing that regression, FinCom, I can go to say fitness. Okay. Fitness data. Then these are the variables. Okay. Or variables. Because this is a regression. This one not regression. So pick this one and paste over here. This is one. Page, weight, runtime, pass. We have 1, 2, 3, 4, 5, 6 here. Okay. And this one, let's see what's gonna happen. Okay, fitness data. Okay, okay. Okay, hold on. Hold on. Into this one, then we have a fitness data in work directory. Yeah, then let's go to the script plot. This is a script plot. See, script plot. Go to script plot here. See, actually actually more than you have a thing, only 2, not even 4. We can with the 2 we can explain that, not even 4. See, principal component. See, script plot according to Kaiser rule. Kaiser rule says, can we see? Value less than 1 should be omitted. Values means like the this one, based on that we're going to do this one based on that eigenvalue. See, according to Kaiser rule, eigenvalue, see, should be eigenvalue. See, eigen, see. Eigenvalue less than 1 should be omitted in the script plot and retain the always values are always greater than 1. See? So see, because of that we can work with these 2. So these 2 actually that we can go with the 2 1. 2 1. Then if you want to explain that one with that not only 4, that based on that one, okay, based on this one you can explain that oxygen with the aid of these 2. And on the other hand, let's go ahead and look at their variation. See, look at the 42. See, this is nothing but eigenvalue is what? This one. See, there's a variance. See, you can remember. I was talking about that one here. See? Sum of that one. Okay, we don't know how they were split. Okay, the sum of the variances are the sum of the variances are the sum of the eigenvalues. Sum of eigenvalues is nothing but the sum of variances. So here, see, you can see this one. See, proportion. Proportion means that eigenvector divided by the sum of the eigenvalues. So the total variation, how much variation being explained by this one, 65%. At least if you want, you can keep 3. See? But it is which is on the bound. Like that. See? Even over here you can see principal component and their proportions. See? Proportions. See? Go this way. See? They go down. See? See? This is summation. See? So up to here, if you want, you can keep up to here, which is almost like a 65% or 70, or 3 of them. See, according to Kaiser rule, you can easily keep 2 more than enough if you stick to that one, to explain that one. So with the aid of 2, not actually 4, according to that one here, you can just explain the oxygen in the population version and sample version of being beta naught, beta 1, PC1, see, PC1 and PC2 enough. And now B naught plus P1, PC1, PC2 enough. PC1 and PC2 enough. But on the other hand, let's run that regression, principal component regression, and see what's going to happen. See, if I keep the number of factors, 2 factors, okay? See? Partial least, okay? You know that the PL stands for that. Partial least square. There is given. See, the percent of area accounted by the principal component. See, number of extracted 1 and 2. See, model effect 18%. See, dependent variable. See, look at the total, almost 70%. Almost 70%. See, variation is almost 70%. And if you want, you can keep 3. See, you can keep 3. Can keep 3. But the thing is, it's not about that. These variables are already there. Okay, I'm talking about the principal component. 3 principal components are thick. Okay, that's what I'm trying to say here. Okay, 3 principal all these variables will be taken into account and then come up with the PC1, PC2, PC3. Okay, PC3 like that. Or you're gonna write by yourself, or you're gonna just check from this regression procedure. See, almost 74%. Sorry, here, see, even the 80%, 80 here, they both places, the model effects and the dependent variables in both places. 80%, can you remember earlier? It's almost like 80% when you run this one. Eigenvalues, the summation, sum of the cumulative values, see, almost, see, 80, see, 80%. If you keep 3, according to Kaiser rule, if you want to stick to that one, keep 2, doesn't matter. So that's that one. But yeah, then that's the homework. But if you go back to that chapter 10 again, that and then I was in the middle of that explaining even the discriminant analysis. Okay, let's get back to that one. Then again, that when we come to this one, that we can remember that the discriminant analysis and the logistic regression being utilized when we have a qualitative variable. Okay. So bank is interested in determining whether the borrowers are creditworthy or not. See, 2 options, dichotomous, 2 options. An investment company is trying to determine the likelihood that certain firms will end up in bankruptcy, while others will not. Yes or no? The personnel director wants to know each employee will be successful or not, successful or unsuccessful. See, in each case, the observation are to be divided into 2 groups, those that have a particular attribute and those that do not. In chapter 7, we work with the X variable like this. X variable. Can you remember gender? Male, female. languages. You can talk about the French and English only, 2 or 3, doesn't matter, categorical. Now, but here we want to predict the group membership. See, we're going to talk about the categorical Y. Standard regression analysis is not really meant for this type of Y variable. No, you cannot use a regular regression for that one. Look at the assumption. Assume we have 2 predictors, X1 and X2. The regression assumption says that for every pair of this one, there's a potential distribution for Y. That's true. The distribution mean is beta naught, blah, blah, blah. The standard deviation is sigma. Distribution form is normal. We know this one. But our situation, it's like this. Let's assume we have a coded Y as 0 and 1. See? Yes or no. The distribution of Y values less than, see? Then it has to look like the one of these things. See? Look at the percentage. Look at the distribution. Okay, this should be flipped. Okay, they have done this way. See? This is either when you get here certain percentage. If it is 30%, the rest gonna go to the 70%. Okay, other way around. Okay, this should be flipped. I think this one has to be flipped because the distribution come to the x-axis, percentage go to the y-axis. They have done this. But anyhow, what they are trying to say that here, if this is 70%, around like a 70%, this should be, let's say that 65, this should be 35. Sorry, here 35, 65, or something like that, whatever. It should be. There are only 2 options for you, okay? 2 options, because that here seems that Y, we draw like this way, okay? We draw like this way. So for the Y variable, see, you have Y variable, you have 2 options, okay? Not X variable. You have for the Y variable, you have 2 options. See? You have 2 options for Y variable. See? So what I'm gonna do is get this one. So Y variable, you have 2 options. Y. Okay. This is Y. You have 2 options, either 0, 0 or 1. See? 0 or 1. For the 1, if you have a certain number of that data, see, the rest should gonna go to this one in the histogram. See? Okay, I'm gonna put 0 here for my listen right. Okay. Draw this one very clearly. So this one, see, this is 0. In a pretty much similar fashion, you can. This is 1. Only 2 options. See, that's it. See, their sum should be what? Their sum should be always 1%. If you put to this side the percentage, sum should be, see, this one and this one. This is 1. This is 1. This is X, either 1x or 2x, doesn't matter. Okay, 1x or 2x. See? It's never been like that, but we did that one for the X variable. For the first time, we're going to do this one for the Y variable. Okay, Y variable. When the regression is estimated, we could get estimated probability. See, 2 problems, bigger than 1 or negative. The normality assumption is violated and sigma is not constant. It's a function of the probability. See, we have a serious situation. Sometimes we get the negative probabilities, or probability cannot be bigger than 1, or normality assumption being violated. Sigma is not the same for all the probability distributions. What we can do, look at, there are several methods that have been developed for this one: discriminant analysis, logistic, and classification. Discriminant essentially using the linear regression, but interpreting the output in a different manner. Logistic is a special type of regression designed to fix the violation. How could we gonna fix this one? We can see technique that try to find a rule for group membership. Okay, let's see then a discriminant analysis. It's a technique for analyzing data when the criterion or dependent variable category. We know that one. Predictor, independent variable, interval. We know that one too as of now. It is a technique to discriminate between two or more mutually exclusive and exhaustive. You know, exclusive and exhaustive, that one I can show you here that very quick. It is something what do you mean by the exclusive and exhaustive. Okay. Look at here. When exclusive means when you have a two events, let's say that you have a two events. Okay. When you have a two events, let's say that exclusive events are events that do not occur simultaneously. A and B do not interact each other in this Venn diagram. See, A interaction, this is called the interaction. See, A interaction, B, see, intersection, notation, see, intersection 0, there's no intersection. Event A, that means P, let's say for instance, at least 1, 5, at least 1, 5. See, at least 1, 5 means like in which direction, which situation that at least 1, 5, see, 11 over 36, some kind of event. So sum should be 4. What this means, when you're gonna roll a 2 dice, when you roll 2 dice, okay, this is based on a certain experiment. When you roll 2 dice, what's the probability of getting at least 1 P? See, at least 1 P. See, 11 over 36. Even B, we're gonna say sum less than 4. If sum less than 4, you never can have 5, no? At least 1 5 you never can have. Because they were thinking about, okay, when you roll 2 dice, if you get 1 by at least 1 5, the other one should be anything. But that combination, how many of them you can see over here? 11 over 36. Some less than 4, 3 over 36. But they do not intersect. That means like a kind of like a, you know, this one very clearly. See, when you draw that, see, when you have this, you can use this die 1, die 2. You have 1, 2, 3, 4, 5, and 6 here. 6 here. Die 1, and the die 2, 1, 2, 3, 4, 5, 6. Then 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. This for the grid. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. All the possible outcome. 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So out of that one, we were talking about here, at least 1, 5, at least 1, 5, at least 1, 5. That means you can get at least 1, 5, mean 5 or 6, 5 or 6. See, one is 5, the other one is 6. So how many of them we have? 5 and 6. 5 and 6. 2 and 6. 2 and 5. 2 and 4 and 6. At least one of them is 6. No, at least one of them 6. Sorry, 5. That's what they say here. Sorry, here. At least 1 5. 11 out of 36. Whole thing is 36. 11. Where they get the 11? The sum is 4. You can see the sum is 4 too. Sum is 4. See, how could you gonna get the 4? 3 and 1 plus 3. 2 plus 2. 3 plus 1. And this one. 1 and 3. 4. 2 and 2. 4. 3 and 1. That means this line. See, 3 of them. That would satisfy the event B. See, there are 3 options for that one. See, 3 out of 36. At least 1. At least 1 means 1 or 6. You can have that one. 1 or 6. At least 1. At least 1 5. See, 5. See, If you have a 5 from 1 from here and 5 from here, 5 and 6, then 2 and 5 and 6, see? Then 3, at least 3, 5 and 6, 4, 5 and 6, this one, see? 6, 5 and 6, 6, no, 6, no, because the 6 is already, see, yeah, 6, okay, at least one 6, at least one. So here, see, here only one, see, at least. See? So you have 11 over there, no? See, get the 11. 2, 2, 2, 4, 5, 6, and here 1, 11. 10, see, 6 and, sorry, here, 6 and 6, 6 and, sorry, this one, missing this one, 6 and 6. This one is 6 and 5, okay. The second one is 5, first one is 6. Second one is 6, both are 6. Both are 6. See, they both are 6. You cannot take that one. So this one you can say 1 and 5, yes, or 1 and 6. Then this one 2 and at least, see, this one, see, 6, 6, 12, see, 11. So that those two never gonna intersect each other, see. If you got a 3 and 6, 3 and 5, at least 1, 5, 3, 5, 3, 6, 3, 5, and 4, 5, 4, 6, 5, 5, 6, 6. So you have 11 of them over there. So they do not intersect each other. So this section and then other section. So that's why they were called exclusively that exclusive. They do not see, can be mutually exclusive and disjoint. What do you mean by that exhaustive? Exhaustive means their summation should be at least, see, always, see, exhaustive means all the events that contain all of the outcome in the sample space. Everything should be within the sample space. See? See? Event A is at least 1, 6. At least 1, 6, or what is that one? At least 1, 6. No, that's not 5, I think. So there's a mistake. Otherwise, it should be 5. At least sum of 4. No, sum of 11. That's a different one. Sum of 11. See, 33. See, I'm gonna get the at least 1, 6. At least 1, 6. 11 of them. The sum of, see, at least let's say that, okay, based on that, this grid, okay, based on grid, you can easily that figure out that what I'm talking about, put this grid and then figure out this probability. But that's not the one I'm really focusing on. That I want to say that when you get the total, this event and their intersection is this event, and if you get their union comes to 1. See, event that contains all the outcomes is for the sample space. See, all the events that contain all of the outcomes in the sample space are for the exhaustive. They were exhaustive. Okay. So anyhow, that, okay, that's the kind of like a rough idea, to get a rough idea, okay, for time being. Okay, you don't have to worry about that much about those things. Okay? So see, so when the criteria depend on, it has a 2 categories, see, adapters and non-adapter categorical variables. So we talk about this one at the time. So let's say that other examples are group size of the independence should not be grossly different. It should be at least 5 times the number of independent variables. See, group size of the dependent variable. Dependent variables group size, each group, okay, whatever the group size, not be grossly different. 80 to 20, okay. See? It should be at least 5 times the number of independent variables. See, independent variables should be normally distributed. Independent variable, okay. Independent variable should be normally distributed. And all variables have linear and homoscedastic relationships. You know this one, covariance, linear, homostochastic, outliers should not be there. And non-multicolor, that means that there are no interaction between the regressive variable, mutually exclusive classification thing. Then that means mutually exclusive means if they belong to one group, they cannot belong to the other group. In the discriminant analysis, what we're going to do, we're going to say that go to the group means of a set of independent variables of two more groups of equal. I'm talking about the two groups, let's say two or more groups. Okay? Their group means, their group means are equals and versus not equal. The group mean is called the centroid. Okay. So let's look at this in this setting. If you apply standard regression to 0, 1 variable, you can perform what is called the discriminant analysis. Y hat value will usually between 0 and 1 and is called the discriminant score. See, when you get the Y hat value, it's always between 0 and 1. We will find a cutoff point C, and if I classify everything above it as 1 and below is 0, you're going to categorize this one into two groups. Okay. How do you do that one? See? First, you're going to get all the discriminant values. See? Look at it. You're going to fit in this one into the regular regression. And then when whatever the regression value is called the discriminant score. Can you remember? We call that one discriminant score. See? Y hat value will usually between 0 to 1, 0 and 1. Okay, because we have only two options. Based on that, given your Y values and based on your X values, you have a two option. Two option means whether this belongs to one group or the other group. That value called the D. Then you go to D, have two options, two groups. Let's say two groups. Go to the one group, and then one group is that group 1, you get the its mean value. Go to the other group, is the 0 group, you get the its mean value. Okay. If they both have both groups have the same size, then your cutoff value is nothing but the average of all the estimated value, average of this value, average of this guy, average of this guy. Or if not, if they're not the same, you go to the weighted average. See, n0 times its mean plus n1 times its mean divided by the total number of observations. That's a total sample. Okay. The classification rule is if you have a DI less than, you're going to go to this group. This one will go to the other group. Okay. When you classify, sometimes they have been misclassified. Okay, that's the one that we can look into that. See, employee performance, you can categorize as two. Y has two options, satisfactory and unsatisfactory. But you have a score on the aptitude test 1, aptitude test 2. For this group, we have, they already categorized. Okay, based on the test 1 and test 2, there are 23 people in the one group. First group means satisfactory group. And the N2 group, unsatisfactory group, 20 people. Okay. Then personnel director has two tests that she would like to use to help determine which future employee will perform in a satisfactory manner and to which will not before they assign to a position. See? Before they're going to assign us a job or they assign any job, any kind of a duties, they have to make sure that this person is performing a satisfactory duties or satisfactory performance at the end of the day. See? The two groups we have, okay. And the current employee classified as a satisfactory one, current employee classified as unsatisfactory 0. Test score results on each of the two tests. The personnel directed task is now to determine how to use this test score to predict the correct classification of each. Correct classification. Sometimes they were misclassified, okay. The parent, okay, let's see what's going to happen. Observation fall into group 1 of interest. This is Y. So this one. And see, we're going to fit in this into that regression model. Okay. And once you regression model, you really need to calculate, see, apply linear regression model, and then whatever the model that you have, see, you're going to write the estimate. Estimate is nothing but D, where D is called the discriminant score or the estimated value of that your regression. Cutoff value is determined through based on that criteria we have. Okay. And see, choose a C as a cutoff in such a way that the probability of misclassification is minimized. How? This is the rule. Average discriminant score for the first group, average discriminant score. Oh, this is the estimated value, you know that. Okay. Sample size are equal. You take the, see, this plus this equal this one. If they're not equal, you're gonna weight it. Okay, weight. Okay. Okay. This is a regular regression model. So let's go ahead and look at this one on this discriminant analysis. I'm gonna get the data, train data. Okay. Train data has a test 1 and test 2, and the Y, see, based on that one, they have grouped them satisfactory group and unsatisfactory group. See, Y has only 2 options, not X, test score. See, 9685 first group, 9688 first group, 9181 first group. There might be some misclassification. We don't know yet. We don't know. That's what we are trying to check. 81, 81, 85. See, almost 81, 85. See, 88, 75, like that. They've been classified already. Okay. Now let's go ahead and run the, let's look at the scatter plot and then how they, if you want. Okay. Between test 1 and test 2 for group 1 and group 2. So look at the group 0 group. See, 0. With the blue colored one. See, higher the test 1 value, higher the test 2 values are. See, they were clustered here, most of them. And these people who are unsatisfactory people always see, lower the value of test 1, lower the value of test 2. See, some kind of a pattern you can see. See, they will see, get together. But there are some mixture. Okay, so these are here. Higher the value of test 1, higher the value of test 2. And those are the ones with the being categorized into group 2. So these two, in addition to that one, there are some others too. See, higher value on this one, lower value on this one, higher value on that one. And then on the other hand, higher value on this one, lower value on test 1, like that. Okay, let's see that how that can be tackled. Then let's go ahead and put the regression on this one and see what's going to happen. Regression, see, the group regression. You have, see, when you write the regression equation, it's a test 1, its coefficient, test 2 coefficient, intercept like that. So when you see that the intercept like that, see, so that's the regression. That regression call, this is when you're going to fit in this one into regression line, as we said over here, we going to be the test, this code. Okay, sorry, this one, see, D. Okay, when you fit in into this one, okay, fitting into this, we got the pretty much the same thing over here. See, same results, minus 5.25, this one r squared adjusted. We looking into those ones, and especially that. See, now what? See, now if you want that, see, 23 and 20 people in each group. The satisfactory group has 23, unsatisfactory group has 20 people. Already the way that it's being classified, and this has been fitted into the regression line, and then with the regression, see, estimated value called the discriminant score. It is the discriminant score. See, that discriminant score will be taken into account when you do the classification for each and every individual. See, again, okay. They're going to classify again. For that to happen, you really need what? You really need the, here you see, they're not the same. See, they're not the same. They're not the same. So if they were not the same, you can use this formula to get the cutoff value. You go to the first group and its mean value, estimated value. Okay, be careful, estimated. Okay, not the raw data. Not the row x1. I'm not interested in x1 or x2. I'm interested in y. Okay, b. Okay, b means y hat. B is y hat for, see, b. Okay, not X anymore. It's been modeled already with the aid of regressive variable. They gone, regressive variable gone. We don't have that one any longer. We have y hat. We play with the y hat. Now we call that one the discriminant score. That discriminant score for each and every group, you can see that they are on d values. There are 23 d values for this guy, these 20 d values for this group. So that one is the one utilized, okay, in order to get the this. That's why they call the fit. See, descriptive statistics of the fits. Fits means the y hat or d. Group this one now 20. Their mean. Y hat means d means, okay. Their means. This is the d naught mean. B naught bar. This is a d1 bar. This is a n naught. This is a n1. See. N naught we know. D bar we know. See. So it's already over there. See, and then put it into the formula. Then you get the cutoff value this much 0.5349. See, then you're gonna classify and say, see, assign if your D estimated value is greater than 0.53, 0, less than this one. Let's see what's gonna happen here. Okay. See, look at the estimated value. See, these are the estimated value. See, these are the estimated value. And each and every individual in this estimated value, see, they are y hat, they are these discriminant score. Doesn't matter whether they are in which group. Now their estimated values are already listed because when you call for the R means residual, okay? Residual, CLI for that confidence level for individuals, CLM for the confidence limit for the mean. See, confidence level for the mean, confidence level for the individual, call the predicted value. See, prediction is greater than mean. You know that prediction for the individual. See, they are, look at the range 2632 to 77 7306. Look at this one. This one gonna go from 81 to 70. See, very short. This one broader prediction interval. This is, see, that's for the individual. This for the average confidence interval. This is individual confidence interval. This is a standard error for the prediction, and this its prediction. See, but let's say that how much this guy has a value in the beginning. In the beginning, how much this guy has a value? Why? Predicted value. See, test score, has that been given? No, they told that simply what? It's 1. Look at, they call this one 1. See, can you remember? It's 1, 1, 1, 1, 1. That's why with the aid of this one, we're gonna go to the cutoff value, which is 0.53. This value is greater than 0.53. That's what it says. Okay. 0.5349, sorry. D1 value, see, estimated value of the first individual has been correctly classified. That's what I want to emphasize over here. Has been correctly classified. Second one has been correctly classified. Has been correctly classified. We keep going like that, okay? And at a certain point, we're gonna see this guy. Look at that guy. Sorry, here. 0.4742, 0.4742, 0.4742. Your estimated value is 0.4742. They say should be, see, 1. So misclassified. It should have been assigned to 0. It's a misclassification. See, their predicted value means the estimated value for the first time I saw over there. So misclassification. This one too, misclassification. Like that. See? So you can see that. See, based on that one. See, less than 0.53. See? Less than 0.53. See, misclassification. Wrongly assigned to 0 group. wrongly assigned to group 1. See, misclassification. How could we gonna find the criteria based on that our how many people? See, we know how to find this one. Okay. So later on, when we go ahead and look into this, okay, that's a regression. Let's go ahead and run the discriminant analysis. Okay, let's run this one. Discrete, train, group, what variables are test1 and test2. Okay, let's run this one and see what we can get it from there. See, look at what they say. 0 people and 0 people. See, 16 and 0 people being classified. See, in the beginning, see the later, the beginning 0 and 1, 0 to 0, perfect. See, but 0 to 0, 16, right? 1 to 1, 1, 1, 18 people. But in addition to that one, there are some people being misclassified. See, 0 people being misclassified as a 1. 1 per people being misclassified as 4. See, 0. See, look at the misclassification. See? Misclassification. See? How many people in 0 group? 20. How many people in 1 group? 23. How many people now in this one? See, 21. There should be 21. See, 21. See, 22. See, this is a contingency table. See, see. Okay. Did you notice that there are 5 people being assigned wrongly? 0 people who are in 0 being assigned to see. They should have been this one, misclassification. See? You can see clearly that one. So that means that people who are performing very well being that wrongly classify into that unsatisfactory group. So let's look at this one. Okay. 16, 4, 20, 5, 18, 23. So the successful employees, 5 out of 23. See, calculation of error rates. We are trying to get the error rates, okay? Error rates, wrongly misclassification. Out of 23, see, as a percent, 5 people being misclassified. See? Misclassified. See? And unsuccessful employees, 4 out of 20. See? 4 out of 20. 4. See? 4 people out of 20. See? In this group, these 4 people being misclassified. See? Unsuccessful employees. See? Misclassified. They should have been in this one, but they put into the one. See? This is a previous one. This is a now. After that, our criteria, after our new the criteria means like a new that threshold value. See, we calculate it. We're not going to calculate that. The program's going to do that one for us. See, it's 4. That's I say unsuccessful employees. See, 4. Successful employee, 5. Only misclassified. See? They were successful, but they were in the other one. See, successful 5 being out of 23. 5 out of 23. Overall, 9 people out of 43 being misclassified. See? Misclassified. It's the same way. Constant and coefficient, discriminant analysis output for the wave. See? This one, see, constant and coefficient. See, now you're gonna go to the group 1. See, look at there that coefficient and the test and test 1. Okay, so this equation can be used to classify any future employees. So now you are interested in classifying the future employee. In order to do that one, you really need a mechanism. That mechanism is where is that mechanism? See, see? It's for the group 0. Group 0. You have a coefficient, this one. See, for the test one, this one. See, this one. See, group 0. You're going to say that this one plus this one plus this one. See, based on your test co, test 2, and then when you get their values, if you plug in into this one, based on that one, you can say that there's a that probability that there's a that the group is going to belongs to this group. See, this group 2, you're going to utilize this one. By any chance that if they're going to plug in into this one and get this value, see, test 2, the group 1 people, see, you're going to plug in here. That means, like, let's say, what are you going to do over there? What are you going to do over there? See? So let's say that somebody's test score like 80 and 90. 80 and 90. Something like that, 80 and 90. If you're going to plug in into this one and this one too, see? And then plug in into this one and see, see? Classify, you can easily classify based on that one whether they're going to go to which group. You know that this score, you know this score will be compared with what? Okay, you're going to plug in here. Okay, you're going to plug in here or here. Okay, here. Then what? How do you compare? How could you know that it's going to go to which group? They say this is the equation. That's the equation for group 1. See? What are you going to do? Can you remember? This is a regression line. Okay, you had a regression line. Based on your information, we fitted that into this guy. Okay, we fitted into this guy, and then we get the y hat. Then when you get the y hat is, see, based on that, those D1 and D naught, see, these two groups, you decide the criteria. C. You need the C value. See, you get the C value. How do you calculate the C value? That already we have a C value. See, calculate a point. See, for this particular scenario, we already done that one. C has been already calculated. See, 0.5349. Then based on that value, you can say that it's going to go to which group. See, they already done that classification for us based on the value. See, if somebody come from that one, they will be evaluated through this one, the group 1 and the group. See, this for the group 2 for the predictions. So sorry, 0 group and C group 1. See? Unsatisfactory group, satisfactory group. Okay. Like so here, see, that's what they say. This is coefficient. Okay. See, that you already generated that one. Then this regression based on the approach does not work if there are more than 2 groups. See, have to be careful. This regression based approach does not work if there are more than 2 groups. A true discriminant analysis computes a scoring function for each group. Each observation is then scored by each group function and assigned to the group with the highest score. For 2 groups, it yields the same assignment as our regression procedure. More general one. The regression-based approach does not work if there are more than 2 groups. A true discriminant analysis computes the scoring function for each group. Yeah, scoring function for each group. Each observation is then scored by each group function and assigned to the group with the highest score. For 2 groups, it gives the same assignment as our groups. Okay. When to use discriminant analysis work? Well, here since we had an error rate of only 20%, it turns out that this technique works well if the X variable are approximately normal. See, X variables are normal. I'm talking about test 1 and test 2. I'm not talking about the Y variable. These 2 variables has to be normally distributed in order for you to use the BA. When not to use the continuous x are not normal, and why cannot transform them to be? If the x variable include categorical predictors, converting them into does not help. So that means if you don't have a normally distributed bell-shaped distribution for test one and test two, you cannot use the concept. Not normal, no. See, then categorical variable for this guy too. No, let's say that gender has been that utilized in order to that discriminate that gender or that any language skills in utilized in order to group into two satisfactory and unsatisfactory groups. That doesn't work. So DA cannot be utilized for that. That's why I think this is a special type of regression designed for modeling a categorical dependent variable. It can be applied to predict data that is not normal law containing qualitative predictors. We don't, yeah, see, when the predictors are not normal, when the predictors are qualitative, we can go to logistic. The y hat function scales so that they always return a value between 0 and that means this time is the probability. This time instead of go that one, you go to probability. See, probability. See, it's a special type. So multi-category version of logistic regression can handle ordinary response variables. See, log linear model describe association structure. Log is a logistic regression. We go to here. For binary response variable y, denote its two categories by 1 and 0, commonly referred to as success and failure. Model for binary data ordinarily assume a binomial distribution. See, binomial distribution. See, look at that one. You get the probability. See, probability for that one for single. See, linear regression. You have one variable. Let's say that you have single explanatory variable. You see, you get the probability of being success. That means eventually it's going to convert to this one. What that means, how come that it's going to come that far? It's going to come that far. Okay? So we have to see that why it's going to come that. This one I have to show you that I can show easily that rather than writing that one again, I can show you how we came to that one. See, you can take something called this see, this form. See, look at this form. This form. Logistic regression formula come like that. Okay, I'll show you. I'll show you that I'm looking for that one. This one should be somewhere easy that rather than writing that whole thing. Okay. Look at I'm going to show you here. See, look at. I'm talking about y. Okay, y. Y may be either success or failure. Yes or no. Each trial, each y, maybe if it is 1, what's the probability of its being y equals 1 belongs to that category of the probability of belongs to that one is simple p. Or its counterpart is q. But if you add those together, that's 1. And then you can say like that. Then you're going to set up this one to when probability as a probability. Y equals 1 is regressed by this one, this model, alpha plus beta. Alpha means beta naught. Okay, beta naught. I'm gonna write this one for my beta naught plus beta 1. Okay, same thing. I used alpha and beta. That's the same thing. Okay, that's the same thing. Regression line. This means simple p. Okay, this means simple p. And simple p, instead of that one, see, y has a 2 options. See, out of 2 options, see, y equals alpha plus beta x. But instead of that one, I'm going to take the probability. I cannot simply say it's in 1 or 0. It doesn't make any sense. I'm going to say probability of that in that particular group is p, is alpha plus beta x. P. Then I'm going to take the odds. Odds. You know how to take the odds. Odds means like that the probability of occurrence divided by the probability of non-occurrence. Probability of occurrence divided by probability of occurrence. It's not going to change anything. It stays the same. Okay. Stays the same. Then I take the log on that. This is called that odds. Okay. This is called the odd. Then I take the log on that one. See, log. When I take the log, I call that one logit. See, here I take the probability. Look at it. Probability of y equals 1. Probability that a particular person belongs to the group 1, or the particular person is passed the exam or something like that. Okay, and its odds of winning and losing. Okay, winning odds and winning logits. See, logits. Probability y equals 1, odds y equals 1, logit y equals 1 is nothing but the log on the odds. Log on odds called the logit. Logit. Then what I'm going to do? I'm going to say, I'm going to bring the log to the other side and push this one that become exponential. And then by rearranging this one, I can rearrange and get the probability back again. And then it's going to come like this. See? 1 over 1 plus e to the negative alpha plus beta x. So the probability of success is given by 1 over 1 plus e minus alpha, this one. Or on the top, you can take the whole thing to the top and 1 minus, that's the same thing they have done over here. See? See? Odds. See, that's what he was talking about. It's graph, it's like this. S graph, logistic graph. Logistic regression has a graph like this. So it is, sorry. That's the probability, okay? Probability of y equals 1. Probability, this is the random variable. So you're dealing with the probability. This is the equation. When you draw this equation, probability on y-axis, this is x, this is beta, b naught, this is b1. If you want, you can look at that. Okay. So that's, it will be described by this one. This is called the logistic equation. It's the logistic graph, S graph. 0 becomes 1, 1 becomes 0. Like this. That's what they describe over here. Sorry, this one. See, logistic transformation, that's the same thing they were talking about. That's the same thing they were talking about. B naught and beta 1, okay. And let's see that on this example, logistic regression, how it works. Okay. So I'm going to go ahead and get the train data, parameter, see, confidence interval parameter and logistic. I'm going to run logistic regression. See? The estimates B naught, B1, B2. In my explanation, I don't have a B naught, B1, B2. I don't have a B2 because that I did that one for only one regressive variable. Here you have a 2 regressive variables because of that one. So if you're going to get this one and plug in into this equation, what do you get? See? This equation, see, B naught plus B1 x1 plus B2 x2. So you can plug in into this one and then make the prediction about the what is the probability if somebody gonna that who will be hired will belongs to the group 1 or group 2. What's the probability that the next item will be defective or non-defective in a production line? You're gonna go ahead and pick the certain sample. You pick 1 by 1, and then later on you planning to go and pick another sample. In that particular sample, next item, what is the probability that next item would be defective or non-defective? Based on here defective, let's say defective, y equals 1. The probability of that one being defective based on that given other criteria. Here, that whether this person gonna pass or fail, satisfactory employer or not. What's the probability that particular person is satisfactory problem group or not? You're gonna plug in into this one and see probability. Here we calculate probability. In classification, in discriminant analysis, we were looking into that we built up two variables to assign that select that correctly select that the the person who been hired into that particular group. You can classify correctly. That's discriminant analysis. Here, you're gonna looking into the probability. What's the probability that particular person gonna be belong to the one group or zero group, one group or zero group. Here we T for zero, this group. If you're interested in the other group, you have to make sure that you solve for Q. Okay, solve for Q, you're gonna get the different formula. Okay. So it's better off to go with the success. We call the success. What you are interested in, call the success. So these are related to the binomial distribution. Y has a binomial distribution while X1 and X2 has a different distribution. Okay. So that everything. There are actually confidence interval and all kind of stuff over here. See? Odds ratio even being given. See? Odds ratio. As I said, that it come through that path, going through that path. That's how they got that one. Right. That's logistic regression. Logistic regression is about that finding the probability of assigning to certain group to group, but you have a very good benefit over here. Here, this benefit would be because it's shape. These are the benefit of look at the apply the binary response rate. For instance, logistic regression can model a voter's choice in a US presidential election, Democrat or Republican, with explanatory variable, political ideology, annual income, education level, and religious affiliation. Whether a person uses illegal drugs, so that's based on that one. Voter choice. See, what is the probability that based on this given annual income, education level, and religious affiliation, probability that person gonna belong to that one, you can figure out. See? Once you get that value, see, all these value, see, you get this value, and you're gonna get this value, this value, this value, and see that what's the probability. How probable that particular person, what is the probability, what is the chance is that person going to be a Democrat or Republican? Let's say that it has been set up like a P equals 1 over 1 plus e to the minus B naught plus B1 x1, see this x1, see, x1, x2, x3, x4, based on these affiliations. And then when you calculate that one, you get the estimated value for the probability. Let's say that you get a 90%. And you decided that it's going to be the Republican or Democrat, doesn't matter, whichever that you are interested on. That's the one we call the success. You have two options. One option would be success. The other option would be failure, okay? Whatever that is based on how you're going to design this one. And then later on, you get an estimate for probability. Estimate for the probability based on what? Based on the values you're going to plug in into this one, you get an estimate. We're not going to do that one. They're going to do this, or the alpha beta we cannot calculate, but the program going to calculate. And if you need the estimate for that one, see, you need see, estimate for this one, their confidence interval plus what else we need. See that they can get parameters, confidence level, we got the confidence level. What else we need? What else we need? CLI, see. This one we got the, let me see this one, let's see what we got here. Yeah, I'm gonna pretty soon stop and then we're gonna continue same discussion, okay? Because in homework 4 and then homework tomorrow I can do the GLM2 and then put the pieces together and we can finalize everything tomorrow. See, here we have estimate, predicted value to estimated value. CLI, CLM. Let's try to get the CLI and CLM on this one. CL confidence limit. Let's say we can get the CLI and CLM. No, it's like go to the CLM only confidence level only. We have to evaluate that one. Okay. Or we have to set up some write like a macro that write another small program to get this done. Because we don't see, I don't see that on this one. I have to check that one. We have only these estimates. We have estimates. Their confidence interval we have. Where's the predicted value? See, association of predicted predicted probabilities. Yeah, sorry. See? Probability of observed responses. We have that one. 93%. See, 6.7 points. See? These are some other different percentages. See, this is almost like a 7%. See, tied one for 0.2. See, 93%. See, concordant and discordant. See, that means see 93% based on that one given values. But these are different criteria of doing that one. We don't have a time to go through all this. We have to get like a rough idea about the point estimate for the test one and test two. See, point estimate, their confidence interval, odds ratio, if you want odds ratio, probabilities and observed responses based on that one, because that's the model. Okay, that's the point estimates for the odds ratio. That, but since we haven't supplied any value, we can get the mainly this one is the one that we can get. We can set up that one because we haven't given that what are the test values are. Okay, test values. For them to, they can estimate based on the test values that they have also too. That's how they came up with this one based on the values that you have. But let's say that somebody gonna come later on and then you want to predict about that one. We don't know, they are test scores. Okay? That's a different thing. Then you're gonna plug in into this formula. Okay? And see what probable that he gonna belong to that group, first group or second group, or in this particular example, whether he gonna be a Democrat or Republican, like that, based on see these two options being modified model with these four variables. But this is logistic. Doesn't matter. You have see look at the quantitative, religious affiliation is qualitative, education level, see quantitative, ideology, political ideology, qualitative. So it doesn't matter. But this method, you feel like this can be utilized even the discriminant analysis. No way. You cannot use the discriminant analysis because of this problem. This is the categorical. You cannot. No. And on the other hand, you have to make sure that annual income and education level to be, if they were numerical, they were normally distributed too, in order for you to use the discriminant analysis. Okay. So anyhow, that I'm gonna extend this discussion and go through the GLM method too little bit. It's pretty much we have talked about that GL general linear model method, and then how that can be applied to our homework and this final exam. So we can finish tomorrow that little bit go into this one more detail again. So if you guys don't have any questions, I'm planning to stop over here. If you have any question on that, your homework, I'm grading that your homework 3 too. And for the final exam and homework 4 and everything, I'm going to give 1 week, next whole week for you to finish it. And you can take your time and finish, or anytime you can finish, and then I can put the grade. But officially, I'm going to plan it to put the grades, not next week, next Tuesday, coming Tuesday, but the following Tuesday. Okay. So if you don't have any questions, yeah, sure, thank you. Yeah, so I'm gonna go ahead and then stop over here, and then you guys have a good night, and then thank you, and then stay safe and be well. See you guys tomorrow. Okay, that's the last day. Thank you very much. Have a wonderful day. Take care. Thank you. Thank you very much. Okay, take care. Thank you.